Welcome back, GL students. We are going to work on now objective 3, which deals with solving linear equations and inequalities. And we're going to try to tackle all this without a calculator, okay? So let's get started. Let me get myself out of the way here, and we will get moving. All right, so first thing we have to discuss are some basic definitions here. The first one is, what is the definition, of an expression versus an equation? Well, an expression is when there's no equal sign involved. There's numbers, letters, there's grouping symbols, things like that, but there's no equal sign involved. This is what we call an expression. An equation is when we have an equal sign involved in the problem. And usually this involves two expressions that are set equal to each other. Okay, and what we're doing is we're finding where do these expressions equal each other, or where do they run into each other. Okay. The next one we're going to talk about is what are variables? Well, variables are when we actually take an unknown value and we represent it by a letter, usually X, A, B, C, D, N, M. There's a multitude of them. Okay. One is a linear equation. A linear equation is any equation that has variables, any variables, and the highest degree that we see in it is a degree of 1. So when we look at something like square root of X, this is not going to be considered linear. X squared is not linear. X to the third is not linear, okay? Anytime we don't have a degree of 1, it's not considered linear. So natural log of X, okay? This is an operation attached to the X. These are examples where it's not linear, okay? What we're going to be doing is we're going to start with first solving equations, and then from there we're going to go ahead and switch over to solving of inequalities, all right? We're going to kind of fly through these because this is a good algebra review. What I want to try to do is encourage you guys to use a 5-step process as we're working through these, okay? I call it DCLAM. Our D stands for distribute. The C stands for you're going to take and combine like terms. L stands for moving the variable to the left. A stands for adding or subtracting, and then the M stands for multiplying and dividing, so DCLAM. You're going to see me work through this list of the DCLAM, and I'm going to kind of check off stuff as it happens. You're not going to see every single one of these steps in every problem, but essentially every problem can be solved using these 5 simple steps, okay? So let's get started. Looking at this first one here, let's go ahead and do DCLAM for this. We look at this and we ask ourselves, does it have the components that we're looking for? Is there distribution here? Well, in order for there to be distribution, there has to be parentheses, and there aren't any. So there's no distribution in this problem. When we say combine like terms, we say, is there anything that I combine on this left side or anything that I can combine on the right side? Well, on the left side, there's an X attached to 4/3, but there's not an X attached to 5. So those do not combine. On the right side, though, there's an 11, and that has nothing else with it. So there's nothing to combine here. Okay? The next step, we're going to move our variables so that they're on the left side. And if by chance there's one on the right side, we're going to move it to the left and get it to join up. When we look at it, the variable's already on the left. There's nothing on the right, so I don't have to worry about moving anything to the left. So now we get to the point where we actually are going to start seeing things, adding or subtracting. What we're going to do is look at the problem and determine what operation took place, and then we're going to do the opposite of it, the inverse of it. So when we see here that it says I subtracted 5 in my left side of my problem here, what we do is I'm going to draw a line here just so we can keep everything balanced. Whatever I do the left side, I do the right side because it's an equation. We want to keep it balanced. I'm going to go ahead and I'm going to add 5 to this left side because that's the inverse of subtracting 5. And whatever I do to the left, I have to do to the right side. So let's go ahead and write this out. We're going to have 4/3 X, and that's going to equal 11 plus 5, which is 16. Now, what happened with that middle portion? The positive 5 and negative 5. 5 minus 5 just canceled themselves out, okay? So we finished that step. Let's move on to the next, okay? What's the inverse of multiplying by 4/3? The inverse of multiplying by 4/3 is actually to divide both sides by 4/3. The problem with this is the way that this works out when we're working with it. If I divide by 4/3 and I go to put this into a calculator, that's going to be a problem for you. Or I just don't know how to do it mentally, right? How do I take 16 and divide it by 4/3? Well, what ends up happening is on this left side, these will cancel, leave me with an X. But on the right side, we did this before. We talked about the idea of keep, change, flip. That 16 divided by 4/3 is like doing 16 times 3/4. which if we multiply this out is 48 divided by 4, which means that x is going to equal 12. The faster way to actually get through this from here to here is, instead of doing the whole keep, change, flip, and all that stuff, realize that if we ever have a fraction in the beginning, if we ever have a fraction right here, we can use the reciprocal, the hand sign of the number. Just flip the number over. And if I had done that right out of the gate, if I had taken and multiplied by 3 over 4 and multiplied by 3 over 4 here, this is going to cancel out, leaving with just a 1. But then I would have had 16 times 3/4, which is the same as what we have all the way down here. So it's just a faster way to get there. Okay? All right, let's jump into the second problem here. We're going to go ahead and do declam. So start with distribution, and in this case, we do have distribution. I know that you want to put 5 minus 2 together and say that that's 3, but you have to fight that urge, okay? Distribution is always going to be our first step. What are we going to distribute here? We're going to distribute a -2 to the left side of my problem there. That 5 comes down because it's before, it precedes at -2. Let's go ahead and distribute. So we're going to distribute here and here, which will give me a -6x and then a -10. That's going to equal 15 minus x. Okay. After we're done with distribution, let's move on to our next step, combining like terms. Do I have anything on the left side that can be combined and anything on the right side that can be combined? Well, on the left side, when we look at this, I've got a +5, a -6x, and a -10. These two terms are like terms. They both have no variable, and so I can put those together. So we should be thinking to ourselves, all right, well, what is 5 minus 10? Let's write that out. So we end up with -6x because that doesn't change, but let's put these two together, 5 minus 10. 5 minus 10 is going to equal -5. Okay, and then we're going to have 15 minus x still on the right side. Next step, let's move the variable to the left. So I'm going to go ahead and move the variables to the left, and we see over here on the right side there's an x over here. Let's get it over to the left. So in order to move things, you either add or subtract it. That's how we move things, adding or subtracting, just moving it. And so I'm going to go ahead and move it by adding x to this side and adding x to this side. When we look at this here, we put things together. We have -6x's, and we're going to add 1x. So I have 6 negatives, 1, 2, 3, 4, 5, 6. I'm going to add 1 positive, and the positive and negative is going to cancel out, leaving us still with 5 negatives. So we have -5x minus 5 is equal to 15, and again, these x's are going to cancel each other out. Next step, adding or subtracting. So let's go ahead and take care of the adding or subtracting. I look at the -5, and the inverse of subtracting 5 is we're going to go ahead and add 5 to both sides. And we end up with -5x is going to equal 20. And then our final step is to deal with multiplication and division. So since I'm multiplying by -5, I'm going to divide by -5. And we end up with an x is equal to -4. And when we look at this, the -5s will go ahead and just cancel out, leaving with just that x that's there. So x is -4. All right, third one. Okay, we're going to start kind of rapid firing this because, again, this should be reviewed. Okay, start with distribution. Okay, so we'll distribute the 2. We have 2x minus 6 is equal to 2x minus 6. And let's pump the brakes right here. So this is what we call a special case. What we see here is that the left side of my equation and the right side of my equation are the same. If these ever happen where you end up with the same thing on both sides, this is called an identity. An identity says that they're equal to each other. What this means is that there are infinite number of solutions. That means that any number I put in should work. Think about why that is. If I put a number in here for this x, I'm going to put the same number in on this right side. And whatever I got on the left side, I'm going to get the exact same thing on the right side. So there's an infinite number of solutions for this. Okay? And you could stop once you see that. Take a look at this next one, though. If I go ahead and distribute here, I'm going to have 2x minus 6 is equal to 2x plus 4. And what happens is, after my distribution, I try to combine like terms. There's nothing to combine on the left, nothing to combine on the right. But then I go to the next step, and I move my variable. So if I move this 2x over here, okay, I end up with 2 x's, and I take away 2 x's. What ends up happening is I have no x's. They're gone. And these 2x's minus 2x's, those are gone. And I get negative 6 is equal to 4. This is, again, a special case. When this happens, my variables are gone. I have to ask myself, do I have a true statement here? And unfortunately, what ends up happening is negative 6 doesn't equal 4. And what this tells us is that there would be no solution for this. Okay? What this means is that these two expressions could never possibly be equal to each other. And if you think about when this might happen, think about systems. Hopefully you guys have done systems. If I looked at this first equation, and I said y is equal to 2x minus 6, and I set the other equation on the right there, y is equal to 2 times x plus 4. Think about what we get. We have y is equal to 2x minus 6, and then the other one is 2x plus 8. If I was to graph these two sets of lines, what ends up happening is that first one, it would begin at negative 6. This one right here. We begin at negative 6, and we go up 2 over 1, and this is what my graph of that would look like. But if I graph the other one and I look at it, it's going to begin at 8, and it's going to go up 1 or up 2 over 1, and it's going to look like this. And when we look at equations and we're saying when are they equal to each other, we're looking at, well, when do they run into each other? And in this case, these two lines have the exact same slope. And what we say is when lines have the same slope, but different intercepts, they're parallel to each other, and therefore they would never run into each other. Okay? All right, next ones. Let's move on to fractional work. Okay, how do we get rid of fractions? I said this to you on our first unit, I believe. It was multiply by LCM, okay, or LCD, okay, the least common multiple. And how do we get rid of decimals? We multiply by 10 or 100 or 1,000. The reason we do that is because multiplying by 10 will move your decimal. Same thing with multiplying by 100, multiplying by 1,000. So like if I did 2.2 times 10, this is going to turn into 2. If I do 0.2 times 100, that's going to move your decimal 2 places, and it's going to become 20. If I took 0.2 and multiply it by 1,000, that's going to turn into 200, right? All we're doing is just moving the decimal, the number of places that there are for the number of zeros. So when there's 1 0 here, we move it once to the right. When there's 2 zeros, we move the decimal 2 to the right. And when there's 3 decimals, we move the decimal, 3 zeros, we move the decimal 3 to the right. All right, but let's look at fractions. Ready? Let's multiply first. Let's get rid of, we have these fractions galore going on everywhere. Get rid of the fractions, right? So look at the multiples of 4, 5, and 10. Okay, those are the ones that we want to get rid of. Look at the multiples. You got 4, 8, 12, 16, 20, 24, and so on and so forth. And then we have 5, 10, 15, and 20. And then we have for 10, we have 10, 20. And then it should jump out at you that these have a 20 in common. Once we figure out what that LCD is, or the least common multiple, what we're going to do is multiply everything by that value. So I'm going to multiply everything by 20. Okay, and watch what happens. When I do 3/4 times 20, what ends up happening is we get 60 divided by 4, which is 15. So now this is going to be a 15x. When I go ahead and do 12 over 5 times 20, this is going to equal 240 divided by 5, which is 48. Okay, and so we end up with minus 48. And then when I have x over 10, which is really 1 over 10, if I do 1 over 10 times 20, this is going to turn to 20 divided by 10, which is just 2. So I have 2x. And then 3 times 20 is going to give me 60. Now my fractions are gone. Now I can just work with some nice clean numbers and go back and do my normal declam stuff. There's no distribution. Let's move my variable. So I'm going to move this 2x over. We get 13x minus 48 is equal to, those cancel, 60. We're going to go ahead and add our 48 to both sides. And we get 13x is equal to 108. And then we take 108 and divide it by 13, and we get that x is equal to a terrible number. But that's okay, we'll just leave it. 108 divided by 13 is our final answer there. All right, 2.4 times 20. Yeah. I made a little mistake, that's why. I hate when I make mistakes. 12 times 20, and then divide that by 5. I mean, oh no, 12 times 20, divide that by 5, we get 4. Oh no, I was right. What am I talking about? Of course I'm right. All right, so it's 108 over 13 there. All right, let's look at the next one. So when we look at this, you can see that there's one decimal place here, there's one here, there's one here, and there's one here. So if we want to get rid of all of these decimals, we can just take and multiply everything by just one decimal place mover, which is by a 10. And that's going to take all of my decimals and just shift them over to the right by 1. So that means that this is going to become 35x, 105, 42x, and then 294. Now I don't have to worry about decimals. We can carry on as usual. Subtract 42x from both sides. And we get 35 minus 42, which is going to equal -7. Plus 105 is equal to -294. We'll go ahead and subtract 105 from both sides. And we get -7x is equal to -294, and -105 gives me -399. And then we divide by -7, and we get x is equal to positive 57. Okay. From here, okay, let's look at this one. Go ahead and pause the video and try it real quick. You're going to go ahead and try to get rid of the 3 and the 15 there. All right, so we have to look at this and figure out, all right, well, how do I get rid of my 3 and how do I get rid of my 15? Okay, so when we look at this, oh, I spilled my coffee. I don't know how I spilled my coffee. All right, so how do we get rid of 3 and how do we get rid of the 5? Well, we got to figure out what's the least common multiple of these. If we look at 3, we're going to have 3, 6, 9, 12, 15, and 18, right? And then we look at 5, we got 5, 10, 15. And then hopefully you can see that 15 is the least common multiple for these. So let's multiply everything by what we just said, 15. Okay. If we multiply by 15, let's do each one of these parts. Ready? 1 over 5. We're going to multiply that by 15. This is going to be 15 over 5, which is 3. So we're going to have 3x right here. 2/3 times 15 is going to give me 30 divided by 3, which is 10. So then we have 10 times x minus 5. And then we have 5 times 15, which is going to give me 75. And now my problem just looks like your standard equation. So we'll go ahead and distribute. We have 10x minus 50 is equal to 75. We'll combine like terms. We get 13x minus 50 is equal to 75. We will add 50 to both sides, and we get 13x is equal to 125. And then we do 125 divided by 13, which does not divide evenly, but we get 125 over 13 for the final answer there. That's it. All right, let's try moving on to our next one here. We've got, for the next part, we're going to be talking about inequalities. So an inequality is when we have an expression that's separated, so a set of expressions that are separated by signs such as greater than, less than, greater than or equal to, or less than or equal to, or even not equal to, okay? So what does it mean to solve an inequality? Well, you're going to isolate the variable just like we did with equations, but then how many solutions can there be? There could be infinite number of solutions or there could be no solutions depending on what ends up happening with your problem. But inequalities means there's a whole bunch of values. Why? Well, when I look at something like this, it says, what are all the values that are true for x is less than or equal to -2.5? This says all real numbers that are less than or equal to -2.5. That means -3, -4, -5, -6, negative forever, right? So what we do is we use a interval notation to represent this, okay? Interval notation, let's write this out. Interval notation uses parentheses when we're talking about greater or less, and it uses brackets when we're using greater than or equal to or less than or equal to. And it's important to note that whenever we have infinity or negative infinity, we are always going to use parentheses because you can't equal infinity or negative infinity, right? It's a hypothetical number that just goes on forever. So we will always use parentheses around those values and then brackets or parentheses depending on what's given to us. So when we look at this one, it goes negative forever. We use a parenthesis right here because I can't equal infinity, right? And right here it says less than or equal to. Because it's going to equal it, we go ahead and use the bracket that's right here. Okay? All right, so let's go through and try to solve some of these. We're going to use some of our strategies that we've worked on, right? I'm going to go ahead and let's get rid of these fractions here. I can multiply everything over here by 6 because that's the LCM for 2 and 3. So 6 times 1 divided by 2 is just equal to 3x. 6 times 2 is 12, divided by 3 is 4, and that's going to be greater than 12. 3x is going to be greater than 16. That means that x is greater than 16 over 3. And if we were to go ahead and write out the interval notation for this, it's going to be x is greater than 16 over 3. So we're going to say 16 over 3 is where we're going to start. We're going to go to infinity because it's greater. I'm not going to equal infinity, can't equal it. And that symbol that's right there is not going to equal 16 over 3. We're going to start at 16 over 3. And we're going to go ahead and graph this. We're saying all the values that are bigger than 16 over 3. So we're going to use an open circle here. And then we're going to actually use a different color. Open circle here. And then we're going to go to the right. Everything that's greater. Okay. Let's go to the next one. Let's go ahead and get rid of the fractions on this one here. We don't want the 5 and 2. So the LCM of 5 and 2 is 10. So if I go ahead and multiply this out, we're going to have negative 120 divided by 5, which is negative 24. That's less than 2x minus 5, which is less than or equal to, hang on, just made a mistake there. That when we do this 10 and this 2, that's going to give us a 5. So we're going to have 5 times 2x minus 5. And that's less than or equal to 40 because we're doing, again, 4 times 10 here. Okay. To go back to this part here, I want to make sure I'm clear on this. This 10, when it gets distributed here, we end up with a 10 times 2x minus 5 over 2. And that 10 divided by 2 is what gives us that 5 that's right there. Okay. All right, from here, distribute. We have negative 24 less than 10x minus 25 is less than or equal to 40. Now you'll notice in here we have two inequalities going on. We call these compound inequalities. Compound means that we just have two different parts and we have an expression that's isolated between these two. But what it means is that as we're solving, whatever I do to one part, I'm going to do to the other part as well. So in normal circumstances, if we pretended like this part was not here, we would just add 25 and divide by 10. We're still going to do that. We're just going to do it to both sides of the problem here. So if I add 25 here, I'm going to add it to the right, but I'm also going to add it to the left. Okay, and what we end up with is a 1 is less than 10x, which is less than or equal to 65. Okay, from here, we'll go ahead and divide by 10, and since I do it to one part, I do it to every part. And we have 1/10 is less than x, which is less than or equal to 6.5. Okay, so now let's go and write the interval notation for this. We have 1/10 or 0.1. We have 6.5. We have our, we're saying all the values that are between these two. And so what we're going to say is 6.5 is going to be the end on the right side value. The left bound of this is going to be 0.1, but we're going to use parentheses. And again, that's because parentheses with the less than, brackets with the less than or equal to. And we're saying for everything that's in between -1 to 6.5. Okay? If we go ahead and graph this now, we're going to be at 0. We'll have 0.1. We'll have 6.5. We'll go ahead and use a closed circle here because we're going to include it. We'll actually be on 6.5. We'll use a 0.1 right here, and then we'll talk about everything that's in between those two. All right, last one here. This is another compound inequality, but what ends up happening is we have an or statement. And what or statements do is they generally go in opposite directions. It's saying it's going to go this way or it's going to go this way, right? They're going to go opposite directions. And when we solve these problems, these are two different problems. Anything you do on this one does not go to the right. It doesn't work on the other problem, okay? And anything done on this problem does not go to the left. These are two completely separate problems. We're working one problem or we're working the other problem. So if I solve this first one, let's subtract 3. We're going to get a negative 30. We get x, we're going to get x is greater than negative 5 when I divide. That's the first part. Or, let's multiply by 6 on this side. We get 3x plus 6 is less than or equal to negative 12. We'll subtract 6. We get 3x is less than or equal to negative 18. We'll divide by 3. We get x is less than or equal to, negative 6. Okay? And so what does this look like? Well, we have two different intervals that are happening here. Let's look at the graph first so we can kind of see it here. So we have x is less than or equal to, greater than, we said negative 5, or x is less than or equal to negative 6. And let's look at these. Ready? We'll go to negative 5. Let's go ahead and make an open circle, and it says x is going to be greater than negative 5. That means it's going to be all the values bigger than negative 5. So it's going to go over here in this direction. For the second part, we're saying x is less than or equal to negative 6. So if we go to negative 6 and we close it, we're going to say all the values that are less, well, less is to the left of this, right? So we're going to go to the left. And you can see these going in opposite directions. So what's the interval of this going to look like? Well, this first part here, when we look at this first part is going to be written as all the values to the left is negative infinity. It's going to go up to negative 6, and it's going to equal negative 6, so we're going to use a bracket for that. For the second part here, this part right here is going to go here and to the right. And so what we're going to say for this part is it's going to be from negative 5 to infinity, not going to include infinity. And because it's only greater, it's not going to have the equal sign, we're going to use parentheses on that. And then how do we join these two? How do we say this or this? We use a U for union. So we're saying there's two different parts to this. That's our interval notation. All right, a couple more problems. Let's jump in on this one. So it says solve the inequality with a negative coefficient. Let's talk first about a rule. When the coefficient of the variable is negative, you must switch the inequality sign when solving. The question always is, well, why? Why do I have to? Well, let's look at it really simply. If I gave you this, I said that 10 was greater than, let's do a different number, sorry. Let's do 20 is greater than 10, okay? It's a true statement. If I added 2 to this, by adding 2, so if I add 2, we get 22 is greater than 12. Is that still true? Sure is, okay? If I subtract 2, look at what we get. We get 18 is greater than 8. Is that still true? Yes. Let's say I multiply by 2. If I multiply both sides by 2, I get 40 is greater than 20. Is that still true? Yes. Let's say I divide by 2. All right, well, if I do that, I get 10 is greater than 5. Is this still true? Yes. So adding, subtracting, multiplying, dividing by a positive number on every side keeps this all balanced. Everything still works. But what happens when I multiply by negative 2? Well, if I multiply both sides by negative 2, I get negative 40 and I get negative 20. And if I kept the inequality there as greater than, is this still a true statement? And the answer for that is no. Negative 40 is not bigger than negative 20. So what do we have to do to make it true? We have to actually switch the inequality. And that is that's the reason that we switch it, because by multiplying by a negative, we generated a false statement. So to keep it true, we have to switch the inequality. Same thing with if I divide by negative 2. If I divide by negative 2, we're going to divide both sides by negative 2, and I get negative 10 is greater than negative 5. Is that still a true statement? And the answer for that is no. So in order to make this a true statement, I have to switch the inequality, and now this becomes a true statement, okay? That's the whole reasoning behind that. So when we look at this one right here, and if I start solving, we have 3x plus 12 minus 4x is greater than 9. If I combine my like terms, we have 3x minus 4x. That's going to give me a negative 1x plus 12 is greater than 9. If I subtract 12, we get x is greater than, negative 1x is greater than negative 3. But then what's going to happen here is I divide by a negative. when you actually see that your divide by, when you have a negative in the bottom, when you're dividing by, that is when we switch to inequality. Okay, that is when this is going to switch to the other direction. And there's your answer, x is less than 3. So we go to 3, open, and it's going to go to the left. Okay? These last two are called literal equations. We're going to go ahead and solve for y. Try not to overthink them, right? If I gave you a problem like this, if I said 3x, let's go like this. Let's say I had 15 plus 2y is equal to 10. And I said, don't actually simplify, just move stuff. What would you do? Well, this 15 you would move over by subtracting 15, right? And so you'd have 2y is equal to 10 minus 15. And I'd say, all right, well, let's get rid of 2. How do I get rid of the 2? You divide by 2, and so you divide everything by 2. And we get y is equal to 10 minus 15 divided by 2. You would obviously simplify this under normal conditions, but in this case, we don't have normal conditions. We don't have any numbers. We have letters that don't really belong together. But the process doesn't change. I have my y here, and I want it to be all alone. So we have to take the ax and move it. If I move it, I'm going to have by is equal to c minus that ax value. Just like we have here. We have minus ax. Here we have the minus 15. It's the same thing, right? We just moved it over. The next thing is, let's get rid of this b that's here. Well, if I divide by b, I could divide everything by b, and we get y is equal to c minus ax divided by b. That's what a literal equation is. It's literally using letters, but the process is exactly the same. Okay? Let's go over here. We're going to solve for w. That means that we have to do three things. We have to first get rid of this 2. We have to get rid of this L, and we have to get rid of this 3, so that our W that's right here is all by itself. So let's get rid of 2 first. Multiply both sides by 2, and we have 2R is equal to L plus 3W. All right, one step down, 2 more to go. Again, our goal here is we're trying to get this W by itself, so that means let's get rid of that L that's there. In order to move the L, let's take away L from both sides. We move that, we have 2R minus that L is going to equal 3W. One more step is left. We're just trying to get this W by itself, and right now it says 3 times W. So how do we get rid of 3? We divide both sides by 3. And what we end up with for our final answer is 2R minus L divided by 3 is equal to W. You're going to use this a lot in chemistry, and we're going to use this much later on with some higher level math, but this is very obvious when you're doing literal equations with formulas like in chemistry, where you have pressure times volume, and then N times R times T. This is a formula which is only involving letters here, and so let's say I want to try to solve for N. In order to do that, you would divide by R and T. We do that so the R and the T's cancel, and we have N is equal to PV And we use this all over the place. Like if I have distance equals rate times time, and I wanted to get rate by itself, I get divided by time. These will go away. We have R is equal to D over T. That's it. So that concludes the notes over section 3. Please let me know if you have any questions or concerns. Until then, you guys take care, and we'll see you next time.